I put a copy of this problem in for starters, just to prompt your memory and see how much you can remember from what you should have done once before. We're actually going to extend from this, and we're going to go into a whole lot of theorems involving angles and lengths relating to circles. But I have to start with the basics to make sure you have the foundations and the knowledge and skills you need to get started. Do you remember how to do this? Do you remember how to solve? For example, if I put a line in here that's parallel to this one, you can find this angle. And a line in here that's parallel to this one, it'll be the same direction, and you can find this angle. Having found this one, you can find this, and so on and so forth. This kind of reasoning is it originally started with Euclid a long time ago. As your textbook says a little above, Euclid's Elements from a long time ago. Euclid's Elements was basically the maths textbook, even the philosophy textbook for 2,000 years, nearly 2,000 years. It was the way you studied maths. Because it's not just about angles and lengths, it's about a way of thinking. It's about a way of reasoning your way to a solution. So, this was just to get you started. Now let me run you through some of the things you have to know as foundational knowledge. So, angles that are up to 90 degrees are called complementary. Angles that are up to 180 degrees are called supplementary. Angles at a point that make a full circle, a full revolution, are up to 360. Vertically opposite angles are equal. Let me see if I can show you what that means. So if I have lines like this angle is vertically opposite this one, and they are equal. And this angle is vertically opposite this angle, so they are equal. Inside any triangle, the sum of the angles is 180. Now it says you can prove this. This is a lead up for specialist maths, so I will talk a bit about proofs. To prove that the angles in a triangle add up to 180 degrees, draw a line parallel to one of the sides. Then this angle must equal this angle. See the Z, alternate angles. And this angle must equal this angle. Alternate angles are equal. But these three angles are on a straight line, so these three angles must also add up to 180, which means so do these three. So that's how you can prove that the angles inside a triangle add up to 180 degrees. Now I expect you do know how to name triangles. At least, I think you probably know these three names. If all three angles are acute, and acute means they're less than 90 degrees, if all three are acute, then the triangle is acute. If there is one obtuse angle, one angle more than 90 degrees, then we say the triangle is obtuse. And exactly in between those two, there's a right angle in the triangle, then we call it a right triangle, sometimes a right-angled triangle. And of course, it's impossible to have more than 180 degrees in any given angle, so I can't have a reflex triangle, and I can't have more than one obtuse angle because that also would give me more than 180 degrees in total. There's another way to classify triangles as well, and that's using the side lengths. I find students usually have more trouble remembering these two names. A scalene triangle has three different lengths. Scale means length. Three different lengths is scalene. An isosceles triangle has two equal sides. Iso, scale, the same scale, the same length. So two sides the same is isosceles. And of course, the two angles opposite those sides are also equal. And an equilateral triangle means all three sides are equal. Equal sides, equilateral. Of course, that means all three angles are also equal, and so they all have to add up to 180, so they're each 60 degrees. I find names of quadrilaterals typically cause more trouble for students. I have a separate video talking about all the precise definitions and names for the different quadrilaterals, so I'll give you a link to that separately. Names for polygons. It's probably worth knowing some of these. You can probably recognise many of them, but numbers up to 10 are worth knowing anyway. Actually, in Australia, we have a 12-sided 50-cent piece. That's a dodecagon. Another word you might want to know. The interesting thing about this is actually that some of the angles inside a polygon. This looks like a fancy magic formula. Let me show you how it comes about. So suppose I start with a triangle. This triangle has 180 degrees in it, and we just talked about how you can prove that. But if I take one of these sides and make it into a 4-sided figure, the 4-sided figure actually has 2 triangles inside it. And those triangles have their angles at the outside of the 4-sided figure, the quadrilateral. So the quadrilateral has 360 degrees in it because it's got 2 lots of 180. Now what happens if I take one other of these sides and make another side? Oh, I shouldn't put it quite like that, I'll move it there. So now I have a 1, 2, 3, 4, 5-sided figure. So this 5-sided figure has 3 triangles inside it, 5 minus 2. If I make myself a 6-sided figure, 1, 2, 3, 4, 5, 6, this 6-sided figure has 4 triangles inside it. And I've still got all the angles are at the outside of that 6-sided shape. So 6 sides has 4 triangles. 7 sides has 5 triangles, and I could keep going. And that gives us this rule. The total size of the angles inside the triangle is 180 degrees times the number of triangles inside, which is n minus 2, where n is the number of sides. And of course, if it's a regular polygon, that means all the angles are equal, then every internal angle will be 180 times n minus 2 divided by the number of angles.